Okay, welcome to chapter 8. Today we will discuss section 7.5. Let me share with you the material for today's lecture. So we are in section 7.5, optimum receiver for binary modulated signals in additive wide Gaussian noise. So this is the simple channel model of AWGN. So we have a transmitted signal SM of T, and then noise is added. Noise is N of T. So the received signal is the transmitted signal plus noise. The noise spectral density is N naught by 2 watts per hertz. So this is the model of AWGN channel. So in our previous lecture, I have briefly described two types of receivers. So, but first we know what is a receiver. Receiver has two blocks, signal demodulator and detector. So receive signal is coming here as R of T. It passes through signal demodulator and then detector. Then decision on transmitted signal is done. So this is the receiver for digitally modulated signal. So in my previous audio video lecture, I have described correlation type demodulator. So you can go through those videos and what is the structure of correlation type demodulator. It looks like this. The received signal is cross correlated and then passed through an integrator and then sampled at t is equal to tb. So this is the final output of the correlator type demodulator. And then we have these conditional probability density functions for the correlator. The conditional probability density function of the correlator output for binary antipodal signal. Binary antipodal, we have already discussed this in what is binary antipodal signal. So they have these two. So the signal, the bit 0 is transmitted in this region and bit 1 is transmitted in this region. And these are the conditional probability density functions. So if S2 is 0, then we have this whole space uh, for S2, and this is for S1, and this is called the probability density function. This is the region that differentiates between this one and this one. So these are the two antipodal signals with energy EB under root and minus EB under root. So binary orthogonal signals, they are uh, the receiver for binary orthogonal signal can be shown like this. So we have a received signal. It is passed through two different. It is cross correlated with two different basis function, phi1 and phi2, and then they are integrated from 0 to t and then sampled at t is equal to tb. So this is the case of correlation type demodulator for binary orthogonal signals. And the condition probability density function of the outputs y1 and y2 from the cross correlator of two orthogonal signals. So we have now y1 and y2, okay, as two outputs. You can see from here. So this thing goes to, so this is the demodulator structure. So the demodulator is cross correlator type. Cross correlation is shown like from this one. So they are cross correlated. Okay, the second type is match type demodulator. So you can go through my previous videos on cross correlator, and I have described in detail some of the examples and solved some problems for you. So there are two videos. In one video we have discussed the theory for cross correlator type demodulator, and in the second video examples are described. Today in this lecture, now I will go through matched filter type demodulator. Again, antipodal signal pass signal through a linear time invariant filter with impulse response h of t. So if you are not familiar with impulse response, you should consult some books on signal and systems. So impulse response is basically when the system is triggered by an impulse and we record the output as a function of time, it is called impulse response. So in this case of matched filter type demodulator, which is a second type of demodulator, so you see the word filter is here and matching is here. So we have to understand what is the matched filter. Since it is a filter, so it will have frequency, it will have time response, which is called impulse response of the filter. So it will be like this, phi tb minus t. So this is a very special type of filter. The time t varies from 0 to tb, and also you can see it is negative of t. So it is time reversal. So tb is our bit duration or symbol duration, and minus t is the time reversal. The output of the filter is usually sampled at t is equal to tb. At the same is exactly the same as the output obtained from the cross correlator. So the sampling is done at t is equal to tb. It's same way as we have done in cross correlator type demodulators. So sampling is done at t is equal to tb. So to understand what is a match type signal, so let us say that we transmitted this signal s of t, and its match filter should look like st minus t. Since the time duration is from 0 to t, capital T, so we put here instead of tb we put here t and minus t. So if this signal, this is the signal that was uh, transmitted. So first of all, we will time reverse this signal. So to time reverse this signal, s of minus t. So basically, its mirror image will come over here like this way, as something like this in the negative time. So this triangle will be over here in negative time, and then we will add t in the time. So then we will this is sorry, this signal was transmitted, then its time reversal will be like this. Okay, so time reverse signal will be like this. So it's a mirror image of this signal. Then we will add in time plus capital T. So we will shift it in this, so it will come over here and it will look like this. So this is a match type filter for the transmitted signal. So signal S of t and filter match to S of t. So this is signal S of t. The impulse response of the filter match to S of t. The structure of this is not shown here. Let me show you the diagram for it. Something like this. So you see, this is a cross correlator type demodulator. Okay. So in this case, we have n-dimensional signal, phi 1, phi 2 up to phi n. Then we have n-dimensional integrators and sampling. So this is a general form of cross type correlation type demodulator. Then we have the match filter type demodulator. So instead of using those expensive these cross correlators and integration, so we are just changing these two blocks by a simple matched filter. So this is a very simple type of demodulator. Now he has shown the example for binary orthogonal signaling, binary orthogonal, and So first of all, let us go through properties of match filter. If a signal S of t is corrupted by AWGN, the filter with impulse response matched to S of t maximizes the output signal to noise ratio. Okay, so signal to noise ratio is given by this expression. So we have N naught over H, since it was N naught by 2, so 2 will come out, above, and then we take the signal energy, so 0 to t and s square of t, so 2 es over n naught. This is actually the definition for signal to noise ratio. So we want to maximize this uh, signal to noise ratio. So he has not shown those expressions, so let me take back to you towards our chapter. So let me share the chapter material with you. So this is a match filter type demodulator in section 7.5.2. So I have described to you the impulse response of the filter. Okay. So instead of using a bank of n correlators mean those multipliers and integrators to generate the variables r of k, we may use a bank of n linear filters. Okay, so n linear filters will look like this. The structure is given perhaps in this book like this. So these are n matched filters. Okay, so this is the general structure for a matched filters. Okay. So then, since we are receiving a signal R, so this will be convolved with our matched filters. You can see this is the convolution of received signal with the matched filter. So Hk as a function of time is equal to phi of k t minus t. This is the definition and this is the label for the filter. So this will be convolved with R of t. So if we convolve h of kt, so it will look like this, t minus tau. So then put the value of h of k as phi k t minus t. So instead of t, we have t minus t, okay? And then this is negative of t, negative of tau. So since time is reversed, so it will become minus t and plus tau, okay? So t minus t plus tau, and k is equal to 1 to n. The next step is to sample this signal. So this is the output of the filters. Yk is the output of the filters. The next step is to sample it. So t should be equal to t, since we are sampling at t equal to t. So this expression, the above expression 7.51.17 will become this. So r of tau, phi of k. So since t is equal to t, so these two will be cancelled, and we are left with only tau. Okay. So in compact notation, we denote it by r of k. Since k goes from 1 to n. So this is one output. K is 1. So then you will put here phi 1 tau, d of tau. And this will become r of k, r of 1. Hence, similarly, you can go from k equal to 2 up to n. Hence, the output samples or the sampled outputs of the filters at time t equal to t are exactly the same as the set of values r of k obtained from n linear correlators. A filter whose impulse response h of t is equal to s t minus t, t capital minus t. So this is the match filter response. S of t is assumed to be confined in the time interval 0 to t. Is called match filter to the signal S of t. An example of a signal and its match filters are shown in figure 7.33. So this example we have described already. So this is a signal, and then it's the match filter which is corresponding to this signal is ST minus T. So the output is Y of t is equal to ST and S of t minus t plus tau dt. So if the signal is S of t, then the response is at the output of the filter will look like this. So S of tau, S of t minus t plus tau dt, which is basically a time autocorrelation function of signal S of t. So signal is time autocorrelated with the original signal that was transmitted. Figure 7.34 illustrates Y of t for a triangular signal pulse shown in figure 7.33. So in 7.33, we are transmitting a triangular pulse, triangular signal. So when this signal is autocorrelated, then we get this expression. Okay. So this is the autocorrelation of the uh, signal itself. So S of t is autocorrelated with itself, but at a little different time, t minus t plus tau. Time reversal plus t plus tau. And when t is equal to capital T, like this one, so this will give us the maximum output. So match filter output is the autocorrelation function of S of t. In the case of demodulator described above, the n match filters are matched to the basis function phi k of t. Figure 7.3 illustrates the match filter type demodulator that generates the observed signal R of t, R of k. This. So this is the typical structure for match filter type demodulators. Okay, now we will go through the properties of match filter. A match filter has some interesting properties. So if a signal S of t is corrupted by AWGN, the filter with impulse response matched to S of t maximizes the output SNR. So this is one of the properties. So to prove these properties, let us assume that the received signal R of t consists of signal S of t and AWGN noise, which has zero mean and power spectral density Sn as a function of frequency is equal to N naught by 2 watts per hertz. Suppose the signal R of t is passed through the filter with impulse response H of t and its output is sampled at t is equal to t, the filter responds to the signal and noise component. So the filter response or the filter output is given by this, which I have already described that it is the convolution of received signal with filter. So tau and t minus tau. Since H is given by, sorry, the received signal is given by S plus noise. So we will put the value of S plus noise here. And we will again convolve these two. S of tau with the HT minus tau. And noise and the filter, they are again convolved. At the sampling instant t is equal to capital T, the signal and noise components are, so this is the signal component and this is the noise component. So we put the value of capital T in place of small t. So this is the sampled version of the output. So this is the signal at signal component and this is the noise component. So what will be the signal to noise ratio? Signal to noise ratio at the output is equal to the energy in the output signal divided by the expected value of the noise component. Expected value of the noise energy component. Okay, so this is, we have to find these two, then we can define the signal to noise ratio. So first we will get the expected value of y n square of t. This is equal to expected value of noise. Okay, so y n square. So y n square is basically expected value of n of tau and n of t, and then you can see what is the noise component again. The noise component is n of t and h of t minus tau. So we have to find the energy in this signal, and then we have to take the expected value because it is random noise. So first we will get the square of noise component, and that then the filter component, this h of t. So expected value of noise will come over here, and then the this h of t minus tau and h of t minus t, because uh, this tau will be cancelled, minus tau or plus tau. So the expected value of this component is delta t minus tau and n naught by 2. So we put here delta t minus tau and n naught by 2 for this part. But this part will be left here. Okay. So n naught by 2 is will come over here, and then 0 to t integration of this delta t minus tau will be 1, and we are left with only one integration, 0 to t and h square of t minus small t, capital T minus small t. Note that the variance depends on the power spectral density of noise and the energy in the impulse response. So this is the spectral density of the noise and the energy in the impulse response h of t. By substituting for y of s, so y of s, what is the y of s square of t? So this will be equal to this component. And then we put the value of this expression at the bottom over here. These two expressions will look like this. So how to maximize this signal to noise ratio? So there is some mathematics involved here. We use Cauchy-Schwarz inequality, that if two signals are multiplied like this and then taken square, then it is less than their individual components. Okay, so G1 square and G2 square. Since the denominator of SNR depends on the energy HFT, the maximum output SNR over HFT is obtained by maximizing the numerator S of signal to noise ratio, subject to the constraint that the denominator is held constant. Denominator is held constant. The maximization of the numerator is most easily performed by the use of Cauchy-Schwarz inequality, which states that in general, if G1 and G2 are finite energy signals, then this inequality holds. So where the equality holds when G1 is equal to C times G2. Okay. So if we want to replace this expression by equality, then we have to put C times G2T. G1 should be equal to C times G2T for any arbitrary constant C. If we set G1 is equal to H of T and G2 is equal to ST minus tau, T minus T, it is clear that signal to noise ratio is maximized when H of T is equal to CST minus T, i.e. H of T is matched to the signal. The scale factor C squared drops out and the expression for signal to noise ratio, since it appears in both numerator and the denominator. So the output maximum signal to noise ratio obtained with the match filter is then given by this expression, 2 over n naught, and then we are left with signal energy. So this is the expression for signal to noise ratio, the maximum signal to noise ratio. I hope you understand it. So again, we are taking G1 and G2, and then we are putting H of T as equal to CST minus T. Okay, so from this expression we will get h of t and s t minus tau. Note that the output SNR from the match filter depends on the energy of the waveform. So if you don't understand this, just use this expression that maximum signal to noise ratio is 2 times ES over N naught. So now we'll look at the frequency domain interpretation of the match filter. The match filter has an interesting frequency domain interpretation. Since HT is equal to ST capital minus T small, the Fourier transform of this relation. So the Fourier transform of the impulse response of the match filter is given by this. So we just multiply it with the exponential minus j2 pi ft d of t. So put the value here and then minus j2 pi ft. So this is nothing but the uh, s star f, because this thing is s star f e raised to power minus j2 pi ft. So there is a shift, frequency shift. So we observe that the match filter has a frequency response which is the complex conjugate of the transmitted signal spectrum multiplied with the phase factor. So this is the phase factor, and then this is the complex conjugate of the uh, transmitted spectrum, the signal in the Fourier domain. S star of f. Star indicates the conjugate, complex conjugate. In other words, hf magnitude is equal to just s of f, because this component will become 1. So we are left with, so the filter frequency response is nothing but S of f. So that the magnitude response of the match filter is identical to the transmitted signal spectrum. Now, if the signal S of t with spectrum S of f is passed through the match filter, the filter output has spectrum y is equal to sf square into e to the power minus j2 pi f t, t capital. Hence, the output waveform is the inverse Fourier transform of this thing. So this will become minus infinity to plus infinity y of f e raised to power j2 pi ft. So you see here plus, so it is inverse Fourier transform of y of f. So put the value of y of f over here, sf square minus e raised to power minus j2 pi ft and e raised to power j2 pi ft. So you see the difference here. This is capital T, this is small t, and differentiated with respect to frequency. By sampling the output of the match filter at t is equal to t, so if we put t equal to t in the previous expression, so t equal to t, so these two will be cancelled. So we are left only with sf square uh, and df, like this. So this is the case of Parseval theorem. We can also write it like this: Parseval theorem. This is in the frequency domain, and this is in the. So this is nothing but the energy in the signal. So the sampled output at the output at t equal to t is equal to the energy in the transmitted signal. So where the last step follows the from Parseval's relation. This is the Parseval's relation, that you can take either spectrum of the signal and scale it and find its energy. So it will be same as taking the signal in the time domain and finding its energy. Both are same. So the noise component, the noise of the output of the match filter has a power spectral density S0 F, and so input spectral density was N naught by 2, and it is multiplied with the filter response, absolute value of the filter response, and then square it, N naught by 2 HF square. So noise is also spectral density of the noise is also enhanced. The total noise power at the output of the match filter is, so this is the spectral density, we integrate it, and so we will get the noise power. So this is the noise power, Pn, minus infinity to plus infinity. So this is the spectral noise density, noise spectral density. So differentiated with integrated with respect to frequency. So putting the value of this expression n naught by 2 hf square d of f n naught by 2 will come out of the integration. So we are left with this thing. So this is nothing but signal energy. So noise power is E S n naught by 2. The output SNR is simply the ratio of the signal power which is given by this expression to noise power. So noise signal power over noise power. The signal power is given by ES square and then noise power is ES n naught by 2. So this expression will become 2 times this 2 will come up 2 times ES over n naught, which agrees with the result given by equation 7.5.25. The previous expression, this one. So he has proved that in the time domain, if we do the analysis and try to get the maximum signal to noise ratio, it is 2 ES over n naught. So this expression is very important for mesh filter. So the only thing you need is the noise spectral density and signal energy to get the signal to noise ratio. So he has done again the analysis in the frequency domain and both results are same. Okay. Now we will go through an example of match filter. Consider M is equal to 4 bi-orthogonal signals constructed from the binary PPM, pulse position modulation signals, and their negatives in the figure 7.12b. So here's those figures are given previously, say figure 7.12. So this is figure 7.236. So you can see what is given in figure 7.12b for transmitting information over an AWGN segment. The noise is assumed to have zero mean and power spectral density n naught by 2. Determine the basis function for this signal set, the impulse response of the match filter demodulator, and the output waveforms of the match filter demodulator when the transmitted signal is S1. First of all, let us go through figure 7.12b. Figure 7.12b. Okay, so this is not given in this one. So let me show you from the other material. So this is our chapter 7. Let me show first 7 figure 7.12b. This is our figure 7.12. Two sets of orthogonal signals. So he is considering these two pulse position signals. So this is S1 bar and this is S2 bar. So these are two pulse signals which are transmitted and he is considering them for this particular example. Okay. Since it is bi-orthogonal signals, so M is equal to 4 and we have dimension N is equal to 2. Hence, two basis functions are needed to represent the signals. From figure 7.12b, we choose phi 1 and phi 2 by this expression. So sometimes these basis function will be given and sometimes these may not be given. So you can easily find them using Gram-Schmidt orthogonalization process. So if these basis functions are given, phi 1 and phi 2, phi 1 has amplitude and 2 over t under the root and time is 0 to t by 2 and then this one is from t by 2 capital T. So under root 2 by t. So this is the second basis function. and he has represented them over here. So these are the basis functions, and our match filter is for this particular case is phi 1 t minus t. Okay, so phi 1, this, if suppose this one was transmitted, so match filter will be this one. So we first take the time reversal and then we shift it by t. So take the time reversal and this signal will come over here and then push it by t. So this will start from t by 2 to t, because half t and then half t will come here. So push will be t, capital T. So this signal will be over here. Similarly for phi 2 of t. So if this is the signal, so it will be, we will first take the time reversal and then we push it. So time reversal, it will come over here, t by 2, 0 to t by 2, and then we push it by t. So the signal will be look like this. So these are the two match filter impulse response, H1 of t and H2 of t. So we are using now two filters there. So y1 of S of t will be equal to this expression, this diagram. How we will get this, and also this one. So we go through this one. So H1 is this expression, H2 is this expression. If S1 is transmitted, the noise-free response of the two match filters are shown in figure 7.36c. Since Y1 and Y2 are sampled at t is equal to t, so after this one, you have to sample it at t is equal to t. So we observe that y1 of s at sampled at time t is equal to this, t is equal to a square t over 2 under the root, and y2s capital T is equal to 0. So a square t by 2 is equal to es, the signal energy. Hence the received vector formed from the two match filter outputs at the sampling instance t is equal to capital T is r is equal to observation vector r1 and r2. So under root e of s plus n1 and n2. N1 is equal to y1 of t, the noise component, N2 is the second noise component at the output. The noise components at the outputs of the match filters are given by this one expression, yk of n. So you take the cross correlation of these two and find the expression ykn at t. Clearly, expected value of nk is equal to expected value of ykn at t is equal to 0. Their variance is the expectation of yk n square t. So en of n of t and then phi t, phi k and phi k. So this will become delta delta t minus tau n naught by 2, and this will be come over a phi square k. So this expression, since it is uh, basis function, so it is this value will be 1 unit norm. So we are left with n naught by 2. So observe that signal to noise ratio for the first match filter is the signal energy divided by the noise energy, n naught by 2. The, so this expression will become es over 2n naught, 2es over n naught, which agrees with our previous results. So in this way, you can analyze other problems given in chapter 7, and you can understand the behavior of match filters. So I will stop it over here, and we can discuss these things more in our today's lecture. So get ready for that. Please go through this video, and we will discuss some problems from chapter 7 during the class session. Thank you very much for watching this video, and let us meet in today's lecture at 6:45 p.m.